All right, let's get started with the presentation. So the presentation is about because this is focused on compilers, so we'll focus on compiler flags for code size and performance. I'll try to make it a little bit interactive, and feel free to unmute because it's a weird setting. Like when I open the presentation, I cannot see the chat, so I just unmute and speak up. That is much better, I guess. All right, so I'll talk about code size and performance. Any guess like why I want to talk about code size first and performance later, like second? Any random guess?
Memory.
Okay, what else?
Less execution time.
Okay, anything else? Code size affect performance in a way. Okay. Any other guess?
Optimizing temporal and spatial localities.
Oh, man, you guys are overthinking. So I want to talk about code size first because it is easier to measure code size. So you'll understand easy. It's that simple. So let's say I have
less number of instructions to execute.
Yeah, means you can measure it. Let's say you do an optimization that is a code size optimization. So you can measure the size of binary, right? Let's say a binary is 10 megabytes and you do some crazy optimization, it became 9 megabyte. You can easily measure it, right? In your machine, local machine, you can measure it. But how do you measure performance? It is the tricky part. So I'll talk about it later. All right, let's move on to some little bit serious stuff. Okay.
Meanwhile, can I ask this question? As in, when in the compilation phases, so code size will be first optimized and then we will come to performance, right? Even though it's easier to measure, but when you are, I mean, the passes happen one after another, right? Sequentially. So, most of the cases. So you first optimize for code size and then for performance, right? And in some of the cases.
It depends. By the way, code size and performance are different things. Sometimes if you do code size optimization, performance will reduce, means go bad. Okay. So it is not like you cannot get best of both worlds in all the cases. But let's move on. So as I said, like what I want to do here is like I also want to give you some motivation. Like why should I even do that, right? That's the first question. Like I want to spend time. I want to spending my engineering effort. I could do something else. But the thing is, why I want to do code size optimization. So here is like a little bit of, these are very approximate numbers. So please do not quote me, but I have taken data from official websites, like well-known websites basically. So let's think of like in terms of mobile application. So when you it's pretty common to have a you refresh your like download your app on a weekly basis. Some people have this enabled by default, so your app gets downloaded in the background, right? But the download is not free. There is some energy cost, so we can assume that it's like very small number, like it's crazy small number. But the thing is, if you see the data about like how many apps were downloaded in 2022, it's like 143 billion or whatever. So multiply them, you see the power consumption just to download the app is crazy, right? And it's only 1 megabyte. So let's say if someone every app saves 1 megabyte, it's like a very ambitious goal, but let's say by magic every app saves 1 megabyte. So the download, you will download 1 megabyte less. Okay, it will be say equivalent to saving so many like 700 million trees. For like you see, like if you're growing one tree for 10 years, you are growing like let's say 765 million tree for 1 year, 10 years. That much savings will be done just by reducing 1 megabyte. Understood? It is just insane how big the impact can be. So don't you can take this seriously. Like, there is some strong motivation here. All right. As I said, like why I want to talk about code size first, because it is easier to measure. So what we are doing here is like whenever we do any optimization, it's just not like hand waving. It's you can think of like it's a science. So in science, what happens? You do something and then you must measure it somehow before and after to see whatever you did has some some useful impact. It is very easy to measure code size impact because there are in Linux you will have some utilities like size is a command and strings is a command. There's a tool by Google Bloaty. You can also see. I'll show examples. I will not just do slides, but you'll see how it works. Pretty trivial. So here is an example. Let's say you are running the size command. Size is a command on your Linux machine. You can try it even now. And you try on any binary. Let's say there's a binary lib standard C++ dot dilib. It will show you something like this, like text, data, obc, others, dec, and hex. Now you most of the time you are focusing on text section. So this dilib has, I don't know, 1.7 megabytes, something like that. Now, if you do an optimization, then this might reduce, hopefully, right? So you can see that, okay, I reduced the binary size by this much. Pretty easy to measure, right? Similarly, there is another tool called strings. It only measures strings. It's not the best tool, but it has some very specific use cases. So it will show, for example, lib standard C++, it will show 2180 string, which is total, like, let's say 36 kilobyte, okay? Now, again, if you do some optimization that is focused on strings, then you can say that, okay, I saved few kilobytes. These are very tiny binaries, so your real world application will be hundreds of megabytes. So don't just look at this number and just make a judgment on that. On the other hand, Bloaty is a tool which is more sophisticated. It will show you a slightly fancier representation, but it gives you more data basically. Okay, and that way it's much more like intuitive. For example, you can see the text section takes 29%, symbol string table takes 25%. So it only makes sense that you want to optimize text and strings table more because it has higher stake in the binary size. So even if you do 1% optimization, you'll get a larger chunk of that. You don't want to spend time on some like a smaller one. Let's say, I don't know, which one is it, like export info, it's like 5%. Don't bother unless you are very expert in that area. All right, now we'll talk about code size optimization, compiler optimization flag. So let's say you're, I don't know, most of the crowd, we are assuming have very little exposure to compilers. So what can you do? The compiler people have given you some ready-made flags. Basically, the first one to try is -os. -os is pretty reasonable because it doesn't, at least the goal is that it will not affect the performance of the app. It will still reduce the code size as much as possible. So OS is very safe to try on any code base. So pretty easy, right? You don't have to do anything. Just add this to your C flags, C++ flags, linker flags, and you're pretty good. Clang also supports a compiler optimization flag called -oz. OZ has a, like, the goal of OZ is to reduce code size by any means. So even if the performance worsens, OZ will still take a decision to prefer code size. Okay, that is the idea. And let's see if I can show the example on Godbolt. Yeah, link is working. Awesome. Let me first focus on the code. Okay, it's a pretty small piece of code. It's a, there is one for loop. I don't know if you wrote this way. Yeah. Yeah, there's nothing fancy going on. It's there's a for loop from 0 to L. L is the limit on the array, and then you're assigning the variable v to array. Think of this like a mem set. Okay, you're doing mem set on in an array. That's it. Very simple. Now the thing is, because it is simple, compiler goes like there's a compiler flag called O3, which is pretty good. One of the most popular compiler flags because this is considered best for performance. So people will use it. Now see what happened here. It's like a compiler just goes crazy. Okay, You see, like it just does all kinds of stuff. It'll unroll the loop, then it'll do vectorization, everything. Okay, looks like there's like 27 lines of code. Okay, compare this to if you use OZ, right? The OZ, how does it look like? It looks like someone just wrote the same code in assembly. Like there's a, you load that, you store that thing and just you branch. Easy, right? Super easy. Well, you see there's only 8 lines of code here. Essentially means it's not 8, it's only 4 lines effectively. So you see what happened here with OZ, right? Your binary size reduced dramatically for this specific case. Okay, that is the goal. Let's move on to the presentation again. Where is my presentation? Yeah, this one. Yeah. Similarly, there is another flag called FLTO. FLTO, it enables link time optimization. Enabling link time optimization may not be super trivial for your code base, depending on how large it is, how much mess it has. So it might require some work. Like you may get like some linker error, some weird runtime error. You might have to do some fixing because if you have never used FLTO, then and you have some legacy code, it'll take a little bit. The other flags like F no unroll loop is pretty easy. You can just put it in any like system. Basically, it disables loop unrolling, so the code size reduces. Next one is called F no exceptions. In C++ code base, you will have exception handling code, right? So this flag disables that. It's not super straightforward, but I don't want to explain too much here. If you can add this flag and make it work, then it will reduce code size because compiler will not generate like all kinds of garbage it does by default. C++, compiler would under the hood, it will generate a lot of exception handling code, and which may not be useful for some application. The last one is fno RTTI. This is for polymorphism, like when you do dynamic cast, etc. The compiler generates stub in the binary. If you use fno RTTI, then you will not have those stuff, but you cannot use them dynamic cast. So slight trade-off there, but you'll save binary size. There are other some flags which are which is like it's a hit or miss. First one I have mentioned here is F function sections. Okay, quite a tongue twister, but what happens is when we pass this flag, compiler will put every function in a separate section. This is to help linker to figure out which functions are dead. So linker can do dead code elimination with this flag. So in principle, it should reduce the code size, but there are some alignment issues that not issues like alignment is like a little bit extra when you do F function sections. So because of alignment, it might incur code size penalty. So plus minus, you may end up with greater than 0 or less than 0. So depending on how your code base is. The next one is F no jump table. What happens is when we write switch statement, compiler will generate a jump table in the binary. You don't have to know what a jump table is. You can just remember it for now. But when we pass this flag F no jump table, compiler will not generate a jump table. It will generate a series of if else statement. So depending on how many switch statement there is in the binary, sometimes you may reduce the code size. Okay. And yeah, those are the flags I wanted to discuss. These are pretty like beginner level, so you might want to try at least OS, OZ, FLTO. These are now most people are trying these days, so you might as well. There are some additional code size optimization flag which you want to get more ambitious. Then there is just like FLTO, which is the link time optimization. There is another one called thin LTO. So this is gives you same effect as a link time optimization, but it does not incur build time penalty. So I'll give you a little bit of overview of LTO. So when we compile C++ program, it is compiled by translation unit. So you have, let's say, you write your program in a.cpp, and then you have another file called b.cpp. So compiler will first compile a.cpp into an object file like a.o, and it will compile b.cpp into b.o, and then it will invoke the linker, which will put a.o and b.o together and produce an output like a.out. Okay, this is the traditional compilation model. When we use FLTO, what happens is compiler puts a.cpp and b.cpp code together, and there is one module, and that gets compiled together. So compiler can see more functions and can do more inlining. A lot of good optimization happens, but it has higher build time. So your compiler has to now deal with a larger file. So there are some algorithms in compiler which starts behaving like, like increases the compile time basically. With thin LTO, it is a slightly like a middle ground. So compiler is still compiling both the modules separately, but they are sharing information. Okay, so that way they get some benefit. Means actually they get most of the benefit, but not all of them. So thin LTO is much more popular for very large application where build time can go like for hours. Okay. Other optimizations are also benefit code size. Let's say GVN hoist, GVN sync. These are like they will save a little bit of code size. Let's say like 1% or 0.5%. There is an optimization in Clang. It is called machine outliner. This can save you like massive code size, like 10%, maybe more. Okay. However, it increases the build time, but it is totally worth the effort for mobile application at least. The next one is called hot cold splitting. This optimization basically splits a function into let's say two parts. One is the part which is more hot in the sense executes more often. The other part executes less often. So, and it outlines all the cold part into a separate part area. That way, the hot part is the code size of hot part reduces, and the cold part can be then you can optimize cold part with OZ. So you get kind of best of both worlds. It requires some engineering, but that is how the purpose of hot cold splitting. One more thing you can do is this is pretty easy to try. Like you change the inliner threshold. What do I mean by this? So let's say we are using -03 optimization flag. So O3 tells the compiler to be aggressive in doing performance optimization. Okay, but you are seeing that the binary size is getting out of hand. So what do? You can inliner is one of the biggest contributor to code size. So what you can do is you want to tell the compiler that do not inline too much, just do a little bit less. So inliner threshold has a number, let's say 200 or something. It's a magic number, and then you reduce that number by, let's say 10. You say 190. Then the compiler will do a little bit less inlining. So your binary size will reduce by a little bit, but at the same time, your performance will be still close to what it was before. So you still save code size, but do not sacrifice a lot of performance. All right, let's move on to performance optimization. Let me see if you have any questions. There is one question by Ruban. It says like, are these flags specific only to LLVM? So yeah, that's a very good question. That's what I did in the first slide. All these flags except OZ, all other flags are applicable to GCC as well as LLVM. OZ is not. In the second slide, all of these are specific to LLVM. Okay, in the second slide. But if you're more curious, then I have just search for code size optimization flag Aditya Kumar in Google. I have presented it in many conferences. So there I have split into different slides. So you have GCC flags and LLVM flags. Because this is LLVM meetup, so I did not want to talk about GCC flags. But I have presented at CPPCon. Let me just give you the link. Where's this one? Oh. Yeah. I will not play the video with this. I'm very confident it has, but if it is not, you can reach out. Anyways, was there another question? Code star flag are a set of lot of flags. Yes, they are. There are compiler engineers which have been working. So, but you don't have to know all of them. You know to know at least 3-4 of them, like O2, O3, OS, and OZ. All right, let's move to the performance optimization. Similarly, like when we were what we talked about for code size, I also want to give motivation on why should we even do performance optimization, right? And unsurprisingly, performance optimization are way more impactful, of course. So I'm giving example of smartphones only, and there is like a lot more computers than smartphone, but this was I could find the data, at least approximate data. So power consumption for, let's say, an average smartphone is 4 kilowatt per year. You know how less that power is? Like it's your typical light bulb will dissipate that much power in like an hour or two. Okay, it's that less of a power. So smartphones are, if in general, like its typical smartphone is very power efficient compared to other electrical devices. Okay, then the question is like, why would I do performance optimize? It does not, like, even if it keeps burning energy all the time, it will probably go from 4 kilowatt hour to 8 kilowatt hour. That's not a big deal. So for an individual which is not part of this crowd, let's say I go to a random person and that person is motivated, like for some reason they think that a smartphone is consuming a lot of power, you know, they might not know the data. So what would I tell them? Like if they are really curious about saving, you know, little bit of smartphone energy, like what would you tell them? Like recently Apple smartphone, they released something that they're saying that we will start charging when there is like environmental friendly power source or something like that. So for an individual person, it is way more efficient to not even think about that thing. Like just if you want to do power optimization for your only personal, like one device, you are one person or one family, you want to just optimize for one phone, a better strategy is to just switch off your light for an hour and you are done for a year. You can never achieve that kind of power optimization by switching off your phone or not using your phone for few minutes or every day. There's like a lot of torture for saving what you can just do by switching off the light for an hour. Okay, it is that much efficient. The smartphones are very power efficient in that sense. However, we have a special crowd here. What we want to do is we are like, let's say I hope you go to like get job at a very big company or a very powerful impactful position. I don't know about powerful, but at least impactful. So as a compiler engineer, we have a leverage to do an optimization that kind of impacts many apps, right? Let's say I optimized a C++ standard library. It is going to go in all the billions of phones. Okay, so I cannot just switch off my light and be happy. So we have like higher expectation, right? So then what we do, this is the data to motivate those people, like people of this crowd. Okay, so yeah, that's what I'm saying here. It's a small number, but there are, let's say, 6.8 billion smartphones in the world. Again, if we do an optimization that saves 1% of power consumption on all smartphone, right? For one smartphone, 1% of 4 kilowatt hour is basically nothing. But the bigger, there is a large multiplying factor, which is the billions of devices, right? So it saves like 2672 gigawatt hour of power, which is like 20 billion tree seedlings for 10 years. So this is like way crazy than the previous code size optimization. Okay, I mean code size was also pretty high. This is like even next level, right? So what I want to this is the most important slide for my presentation. Like I want to give you a motivation to work on this. Like there are people who are these days there is a lot of environmental friendly, like global warming, climate change, those things are going on. But as a compiler and software engineer, what I can do is like kind of unachievable by most people on earth. Like I can do a few lines of code that will achieve way more power savings than people can even imagine. You can keep planting trees. We can never plant like 20 billion trees. Nobody can do that many trees, right? But I can do an optimization that can actually be equivalent to billions of trees. So it's insane amount of impact that we can generate. And so I'm not just bragging these things. Many people have done it. I'll show you examples later on. So stay tuned. Okay, let's go to the. This is the real stuff, right?
Hey,
So,
sorry to interrupt.
Yeah.
But is there any? I mean, this is a completely different perspective on performance optimization that I'm hearing for the first time. So, is there any research that is being done on this that is relating to like performance optimizations and actual environmental impact?
Yes, not directly, but in the, so you see these links right in the bottom.
Yeah.
All these 3 links. You click on this. So I did not pull this data randomly. There is a website called
No.
epa.gov.
I'm not. I'm not doubting your sources.
Yeah.
I'm just asking.
Yeah. 1 second. So epa.gov, you go there and you can put the number that, let's say I save 1 gigawatt hour of energy. Then what is the equivalent? So the last table, this equivalent, I got from there. Actually, I should show you. It's pretty interesting website. So let's just do this. All right, let's see. This is a government website. Okay. So what you do is you plug in number here. Let's say emission data. Sorry, energy data. Kilowatt hours avoided. So let's say that's what we are doing, right? As a performance engineer, we are kind of avoiding that many power. Let's say I avoid 1000 kilowatt hour. That means like 1 megawatt hour of energy, right? So convert the data. And there's lots of things, pretty interesting numbers. So if you save 1 megawatt hour of energy, then it's like equivalent to 0.797 metric ton of carbon dioxide. But the data I pulled in was, so it is equivalent to saving 0.84 acre of US forest in 1 year, right? You saw the number right here. So these are the numbers which I'm putting. So let's say I save, like, let's say, how many zeros are there? Yeah, 1 million. So okay, so 1 gigawatt hour, right? 1 gigawatt hour is 845 acres. That's a lot of trees, right? Similarly, 11,000 trees here, 11,000 tree seedlings. Those are the numbers I put in there.
Right. Thanks.
Yeah. I mean, it's a valid question that who is doing this? We have to do it. Who else will do it? All right. Let's. These are the things that will enable you to do that, right? So again, very similar stuff, right? You don't have to worry. Remember all the 20 optimization, and these are not like crazy things that it is difficult to remember. You don't even have to remember. Just go and look at my slide, or there are other people also. You can look at their slide also. So compiler optimization flag, let's say O2 and O3 and OFAST. These are the flags that are meant for performance optimization. Okay. pretty easy to remember. Let's say in your code base, you have O2. I have seen in many places where people will just use O2 and think that, oh, O3 is risky, it may crash the compile app, and it's like it has bugs, blah, blah, blah. But they are thinking like 15 years old, with a 15 years older like mindset. These days, as a compiler engineer, we are not putting like bad things in O3. There are very good optimization there, and people should try it out. Many cases, what happens is they might have bug in their own program, like maybe it is unmaintained or like nobody bothered to rewrite or something, right? 1 second, just, yeah, I don't know what happened. Abhijit says, yeah, anyways, so yeah, but people should try O3. And there is another one called OFAST. OFAST is not like a next level of O3. OFAST means O3 plus one more thing. Okay, I don't want to explain too much here because that's not the route, but you can try OFAST also. And let's share one more example. All right, very small example, right? Let's see. And if you have never done compiler optimization, you'll see at least like a slight hint of how bright compiler can be. I'm assuming this is visible because I shared the whole screen, right? Is it visible?
Yeah.
It's code. Okay, let's see. So very simple code. There's a function baz, and if x is less than 10, you call foo. If otherwise, you call same function foo x plus 2. Okay, with x plus 2. So only the parameter has changed, but the function call is same. Okay, let's see now. At O0. O0 is, if you do not supply any optimization flag, it will be O0. So if you're working in a company, try to find out places where there is no optimization flag and just slam something, you will get a free improvement. And you might think that, oh, there are so many engineers working, why would they have this? It happens many cases. I have seen this, I have done it. So you will be surprised. Okay. So you can just start spending some time in the code base, and with like 3 characters dash o, actually 1 character, if it is O0 and they put 3 instead of 0, just changing 1 character, they give you crazy improvement. So here is the code. I'm not expecting anyone to read this, but you can think that this is like large and just useless load and stores, right? When we supply O3, it becomes like 10 lines of code, and you see what it does is, okay, I think I should have explained a little bit here. So think of this like there are 2 branches, if and else, right? And you have call here, call to foo. So basically it says if x is less than 10, go here, call foo. And otherwise go here, do x plus 2 and then call foo, right? Essentially. Here what it does, you see, there is only one call to foo. But how does this happen? What it did was it only made a decision based on x is less than 10 or not, and change the parameter itself, and then call foo on the same thing, right? So compiler got clever, right? So free optimize, you got like, see, such a nice code. And in general, it couldn't be done by software engineering also, right? You can just have done here, let's say, you define a variable. What you do is comment this out, do nothing here, and here you do x plus equal to 2, right? And then call foo on x. So essentially what compiler did was this. But yeah, same thing, like same thing what I did with by hand. Similarly what that compiler did. But again with O2, still you have like useless load store because it's O0. It did not do any optimization. Okay, so you got the idea. Then yeah, you can try with other things also. All right, presentation mode. Other optimization, LTO, FNO, exception, FNO, RTTI, these help with performance also. I already talked about it. Then there is all this I shared before also. But the nice thing about these optimization are they help with code size, they help with performance also. But so most of them are not enabled by default, so you have to supply this flag extra. I'll talk about this hot cold splitting also because this is interesting for two reasons. This is a very modern compiler optimization. And the second interesting reason is I wrote it. So that's the two interesting reasons. Okay, let's see. Here is a code, pretty ugly code, but just to give a motivated example. There is a function baz. What it does is if x is less than 10, then call foo. Otherwise calls bar like 3 times, just for the sake of an example. However, I have added this attribute likely. Does anyone know this flag attribute likely or no?
The likely flag basically says that a branch is more likely to be taken. So this would optimize branch prediction. Am I right?
Yes, exactly. That is correct. And this likely attribute is it's C++, I think C++ 20. But in other compilers like older compiler also and C also, it supports an attribute called built-in expect. So built-in expect. So you can search for it and see how it is used. It gives you the same effect as attribute likely unlikely. Okay. In fact, built-in expect has more powerful. So if you're you don't want to use attribute likely and unlikely everywhere, it'll make the whole code base look very ugly. Okay, you don't want to do that. So you don't want to make your code base ugly. That has a real impact on developer experience. So you only want to do this on hot pieces of code. So you figure out that some part of code is very hot, only do there, not everywhere. Anyways, I have to move fast. So just sharing an example here. So with O3 and O3 with hot cold splitting is the middle one. And what it did was this entire else branch, it made to a separate function built in cold. So all the cold part came here and the original function is only like 14 lines. Compare this to O3, the function is like 22 lines. So overall the lines of code with hot cold splitting is higher, but the useful part, the hot part is smaller. So you have I-cache locality, better I-cache locality. Okay. Similarly, you can try other flags also. There are plenty of examples online. All right, move to the next one. Okay, so those are the flags I wanted to talk about. Then same thing, like when you do an optimization, you must know how to measure them. Otherwise, what will you tell people or yourself? Like you did something, what happened? What was the impact, right? So there are some tools. I will give you a very brief example. Let's say there's a tool called Valgrind. It is a very old tool, but it is still useful in the sense you don't have to learn too many things. So you can just launch Valgrind, like your app under Valgrind, and it will show you some few things. For example, let's say this is one run of Valgrind. So it shows instructions, read, data, read and write. Okay, and it is you have some numbers here. The nice part about Valgrind is it is deterministic. So if you run the application again, it'll give you the same number. Okay, so it makes it easier to measure in the sense count. So you did some optimization, then you run again, and you see that some let's say reads got less or writes got less. So you have some notion of that some optimization happened. This may not precisely have reflect in the real world, but still it is a very good starting point. Okay. Other tool is Linux Perf. It is very popular these days. Linux Perf, basically there are 3 commands which are you might want to learn, at least in this session. There are many other commands, but these are good starting point. Perf stat, perf record, and perf report. Perf stat will give you an overall aggregated summary of what this application did, like instruction count, cache misses, etc. Perf record will show you, it will record many places, many parts of the code, and then give you a kind of a profile, and you can see which function is hot, which is not hot. Then you can dig into assembly line and say which assembly line of code is hot, and it will also give you annotation also if you have debug symbols. So you can, it's pretty powerful tool. And perf report is basically to show the data from perf record. So here is an example of perf stat. So you see, this is a very aggregated summary, like how many page faults were there, then how many instruction branches, branch misses, etc. So let's say you do an optimization, and then you compare before and after, you see some changes here. Okay. But the thing is, this is not deterministic. So if you run the same app again, you might see very different numbers. So slightly, that's why performance is not very easy to measure, and you have to learn a little bit more about measuring the performance. However, if you do like a crazy optimization, you will definitely see a large difference in the number. Okay. So similarly, this is perf record. So perf record shows like which line of code is hot. So like it's like a histogram. So 18%. So load, this line has like, is the most important one basically. So if you can optimize this load, you are in a very good shape. Okay. All right. Let's talk about analyzing system performance. What does this mean? Whenever you are working on software optimization, it is not like one line or one loop or something. It can be in some cases. Let's say as compiler engineer, many times we are optimizing a benchmark, and in benchmark there will be loop. You can optimize the loop. You don't have to think about system. But in real world, let's say when I was working at Facebook, I have to optimize the Facebook app itself. So there is no like one loop which you can optimize and be happy. You have to think about like a large piece of code base, right? How do you even think about it? I'm not giving you techniques here, but I'm just giving you thought process, because there are many tools that can give you things that I'm talking about. So first thing you have to think about is vary only one component of the system at a time. It's pretty common sense, and that is, it is actually very useful and not always practiced. So you want to know about this. If you change only one thing in your experiment, like each optimization, think of it like an experiment. So you can see before and after, right? So you have only changed one thing, so you have higher confidence that what you did, what optimization you did, resulted in that delta of when you measured it. Okay, because there is already too much noise, so you want to reduce the number of variables as much as possible. And again, you want to run multiple times. Similarly, there are things like disable frequency scaling. I don't want to talk about it, but just for completeness, I put it here. Then you want to look at dynamic profile, compiler logs. Compiler logs can be helpful also. Like there is a flag in Clang called rpass. It'll rpass analyze. So it'll show you like where the compiler missed an optimization. So that way you can go in the code base and maybe do some changes that compiler can do that optimization. It is very useful in vectorization, because compiler cannot do all kinds of vectorization, but it gives you hint that why I was not able to do it. And maybe you can change the code to help compiler and get crazy improvement like 4x, 10x, something like that. Vectorization is very powerful. Then other part about system performance is you want to measure it over time. This is not like a one-time thing you did and you sit back and relax, enjoy the flight. No, you did, and then someone will write the code, it will go back to some weird place again, so you have to do again. And performance hotspot also keeps changing. Like after a year of development, something that was not important before will become important, right? Like 5 years ago, not many people were using video, but now people were using stories or messages more. Now people are using video. So if you're just sitting for 5 years, you will be losing on performance. These days you have to optimize video more, right? Think of things like that. Okay, this is a pretty important slide, but I want to see if there is a question. What about PGO? Yes, it will record. So yeah, I should move on. There is not a lot of time. What happens with performance optimization is these are not deterministic numbers. Okay, when you run multiple times, you will see multiple different numbers. It might vary by 1-2%. But I talked about optimizing 1% of all the mobile app. How will you measure 1% impact when the noise itself is 1-2%, right? How do you reduce the noise? So you have to deploy statistical techniques, right? And in the statistical technique, there are many pitfalls. Like these are not like very exact algorithms. It's not like a sorting that you sort it and it's always the same result, right? So how do you do when you measure, like let's say 100 times, you have to figure out which number will you pick. Will you do an average? Average is a very bad number. You want to have a central tendency. Average does not have central tendency. So you want to use median. Mean is the average. You don't want to use mean. You want to use median. Okay. Similarly, then you want to then you, like let's say you got more mature, you want to do like some more sophisticated performance analysis. So you use quantile values. Quantile values means where do you median is like a p50. Okay, it's like in the middle of a sequence of data, right? But let's say you want to care about p60 or p75. So think of like a percentile thing. Okay, that way you can focus on you have a different view of data, right? What do I mean by p75? P75 means 75% of measurements were below or above in that sense. So if you optimize for p75, you affect 75% of use cases, right? So it depends, like 75 or 25, depends on how we are measuring it. But like having quantile value is much more like more mature than median value. Okay, then you want to find outliers. Let's say there is like 1% of customer who are getting crazy performance changes. So you want to see that is this the norm, or is it like an outlier? How you have to filter those things, otherwise they will affect your measurement numbers. Then weighted sample for combining historical data, because something that was important 1 year ago may not be as important today. So you want to have that data, but do not have same weight for today's data versus 1 year old data. So you have to have some weighting. All right, how much time we have? Just confirming, you means percentile score. Yeah, something like that. Search for p75 like on Wikipedia or something. You'll find it. Means these are getting more popular in last few years. Previously people will even use average, and then someone came up with a stupid idea like geomean. Geomean is as worse as average. Why would people use this? So we want to use like some like median, for example. Median is much more better. Do we have time to okay, I'll take 5 more minutes just to show this is like now real world exercise. Okay, first case study. This is an example, very short example, almost everyone can understand. What am I doing here? I'm copying one vector to another and returning 10. That's it. So can anyone say like what happened here? Like what can we do here? What is the problem? Or means what are the opportunities here? Anyone? It's a simple code. All right, I'll just take the lead. Essentially, this copy, it's a dead copy. Compiler should not generate anything. It should just return 10, right? That is my expectation. But you see what compiler did here. Like all the weird things it did for nothing, right? This was 5 months ago. Okay. After optimization. So I did this optimization a few months back, like April or May. After this, it is still not the best code, but you see all the weirdness went away. This bold line on the right side, that is the code for basically the important part of it. You still have some checks before and after, but all the weird loops went away. There is no copy anymore. Okay. Next exercise. This one I want everyone to participate. It is pretty easy. So you have three code base, three pieces of code. All of them are doing the same thing, right? You have a vector, you are iterating on vector, and you're calling a function on each element of vector. I'm sure everyone here would have written some code like this. Maybe someone preferred one approach over another, but there is no programmer in the world who has not written a code like this. It's just impossible. Okay. Right. If you have not using C++, then you might be using some other language, but it's very common to use this pattern. You're iterating on an array, you are calling a function on one element on array, right? But let's say for C++ program, because that's what we care about here. What do you think? Which one is the most efficient in terms of performance, or all of them are equal? Any guesses? Anyone? Guys, please say something. All are equal. So someone said range-based for loop is more efficient. Okay. Any guess? Iterator is more efficient. Iterator is the middle one. Okay. One said all are equal. I mean, I would love if all are equal, but that did not happen, right? That's why we are talking here. Anyways, let's see what happened. So the first one is on the top right. So you're using this, like you're using size type. This is the worst code. Okay. First one is the worst. Why? Because you see this tiny little piece of comparison here, I less than v dot size. What happened is v dot size compiler is unable to figure out that v dot size is loop invariant, and it load v dot size all the time. Useless load in every case. Okay. The iterator case, you have v dot begin, v dot end, I plus plus. You still have an extra add. What is extra here? Move, call, add, comparison. Okay. So these two are same because the way I wrote the code. Oh, okay. Thankfully, iterator and range-based for loop are same. I don't think it should be same. There is an extra, yeah. So there is, you see the comparison here in the iterator based, there is RBX plus 8. So, but in the last one, it is RBX R14. So it's a much simpler comparison in range based for loop. But in the iterator one, it's like tiny little worse. Okay, these are still pretty close, but range based for loop is the most efficient. Why? Because in range based, you have already cached the v dot end outside the loop. So you are comparing with, I guess, a constant pointer, basically. Okay. So range-based for loop become much more efficient. It is like kind of, what is the question here? If v dot size is loop invariant, then won't the compiler optimize this by unrolling it outside? Yeah, compiler cannot establish that because the way vector is written. It's a very big problem actually. And how many people would know about it? No, not many people. And everyone makes a lot of mistake because of that. Abhijit is saying because of comparison between a load and a register in the two cases, load causes a slight overhead. I mean, you have to have load because you're loading one element, each element in one iteration. There's no way getting around that. But the comparison here is like RBX plus 8, but yeah, so you're doing RBX plus 8 and using that pointer. You're using just RBX plus R14, which is like ready-made. So yes, the last one, that's why it is more efficient. All right, let's see. This is like this is still a problem. Okay, I wanted to show this one because of that. All right, I guess the only references are there, so there is nothing. I can just stop sharing. You have any questions? Anything? We are basically done. Any questions? No.
I had a small question. Suppose, like I was recently working on an issue. In
Hmm.
that issue, we were trying to optimize the less operator of the STD library. So I had no way of benchmarking the results online. Uh, is there a way I can do it online, or I have to use Valgrind only? Because I never knew I could use Valgrind so easily, or I was introduced to Valgrind in this talk as only. So
Yeah, means if you can use Linux perf, I would suggest to Linux perf. Okay, but Valgrind is like a good starting point. If you have nothing, then you can just use Valgrind, and Valgrind only works on Linux machines, not on like Mac or
yeah,
something. Yeah, but if you do not know any other tool, then you just use Valgrind. I'm not discarding them. It's also a very good starting point for people who have never done measurement, because Valgrind numbers are deterministic. So if you run
yeah.
again, it will give you the same number. That gives you like much easier to have confidence there, right? So
Agreed,
that's fine.
agreed, agreed.
Yeah.
So because of the consistent results, right?
Yeah, yeah. And but the only thing is, if it is a large application, then Valgrind will be slow. Okay. So
Got it, got it.
depends on how, or like what application. Yeah.